Okay, and now I think we have sort of the tools we needed to get to the important point, which was differentiating improper integrals. So we're going to start out with a function f that's continuous, and we're going to assume that the integral of f over the entire real number line, so integral from minus infinity to infinity, exists. So in particular, that means that it's finite. And now I want to consider a function b of t. It's a differentiable function, and I'm going to define a new function g of t, which is going to be the integral of my function f from minus infinity up to b of t. And I want to be able to compute g prime of t. And so it's sort of like taking the derivative of a definite integral. It actually doesn't end up being too difficult. So all we're going to do, because we assumed that this integral exists, that means I can pick a point somewhere in between. And I can write g of t as the integral from minus infinity up to that point, plus the integral from that point up to b of t. And then, because I'm free to choose that point, I might as well choose something that's easy to work with, so I chose 0. And so now I just want to take the derivative of g of t. But since the first term, so if I look at this closely now, this is it's an indefinite integral. So the integral from minus infinity up to 0. But there's no t's in this first term. So as far as I'm concerned, when I'm taking a derivative with respect to the variable t, this is a constant. And so when I take the derivative of that with respect to t, when I take its derivative, I'm just going to get 0. So to compute the derivative with respect to t of my function g of t, I can just ignore this first term, and all I have to do is compute the derivative with respect to t of the integral from 0 to b of t of my function f of x. But notice what happened now. So the problem that we were trying to deal with is that we had an improper integral. But because of this, the limits here are both finite values. So this is the integral that we already know how to take the derivative of. This is just we use exactly the same rule I talked about in the, I guess it would be number 7 today, how to take the derivative of a definite integral. And on top of that, we're lucky that the bottom is 0, so we only have to use half of the formula. So g prime of t is just going to be the derivative with respect to t of the antiderivative of f evaluated at b of t minus the antiderivative of f evaluated at 0. And this is just the result from differentiating a definite integral. So I know that that's f of b of t times the derivative of b of t. So f of b of t times b prime of t. And then to do the same thing for the lower limit, or we can do the same thing for the lower limit. So I'm just going to, instead of g of t, I'm going to have h of t, which is exactly the same thing, except that now it's my lower limit that's a function of t rather than the upper limit. And so I'm still going to consider integrating this function from a of t to 0, and then adding on the integral from 0 to infinity. And then when I take the derivative of that, this second term now is going to be the constant, so that's just going to go away. So the answer here is just going to be the derivative of this first term. And so the only difference we're going to see is just because when I do this part of the fundamental theorem of calculus, now my function a of t is on the negative side. So I get the same answer as I got for the upper limit being the function, except now it's just going to be minus f of a of t times a prime of t. So now we have a very simple rule for taking the derivative of an indefinite integral. And let's see if we can put that to work. So I'm going to look at something called the delta of a European call option that I'm going to price using the Black-Scholes formula. And so the Black-Scholes price for a European call option, so this is the simplest possible one to look at, on a non-dividend paying asset, so this could just be a stock, for instance, with a strike price of 1, has a volatility of 20%. So this means the volatility of the returns on my asset, and I'm looking at 3 months to maturity. And so again, the reason I'm putting all of these real numbers in here is just because the Black-Scholes pricing formula, it's a function of several variables. I'm going to make it into a function of a single variable s, which is the current price of the asset, just by plugging in actual numeric values to all of the rest of the inputs. And so this is the pricing formula. So I have s times this function phi evaluated at d1 minus e to the minus 0.01 times this function phi again evaluated at d2, where d1 of s is just going to equal 10 times the log of the current stock price, so 10 times the log of s plus 0.015. d2 of s is equal to d1 of s minus 0.1. And this function phi, so this is where all of the math we've been doing for the last 2 lectures is going to come into play. This function phi is defined as the integral. So this is a capital phi, where in the font I'm using, it's drawn just with a vertical middle line. And the lowercase phi is its derivative, which has a slightly slanted line. So I'm going to integrate lowercase phi from minus infinity up to z. And lowercase phi, this is a probability density function for a standard normal distribution. And this is the mathematical form that it has. So in order to calculate the price of my European call option, I'm going to need to be able to do mathematics with this function capital phi. But this is a function that's sort of famous for not having an antiderivative. So you can't actually write down a formula for the value of this integral. This is the simplest that I can write it down. So in order to actually price these things, you have to use a computer to approximate the value of this integral. But when we do mathematics with the Black-Scholes formula, we still want to be able to get analytical results. You know, if I try to do everything numerically, then you run into problems of, you have to be very careful of, you know, as you continue to do calculations, are you accumulating any round-off error in your sums, things like that. So what we would like to be able to do is actually compute derivatives of the Black-Scholes pricing formula and get the correct answer theoretically before we actually have to start plugging in numbers to the formula. And so the delta of a European call option is just the derivative of the price. So the derivative of the pricing formula, so in this case C of S, with respect to the asset price S. And it's denoted by this equilateral triangle is a capital Greek letter delta. And so this is the derivative that I'm going to try and compute. So it's already kind of complicated, and it's much, much more complicated if I don't plug numbers into it, because as soon as I plug the numbers into it, I can do some math, and a lot of them combine together. But it's still complicated enough that I'm going to try and compute the derivative of this term by term. So first I'll look at this term, and then we'll look at this term, and then we'll try and simplify our answer as much as we can. So for the derivative of the first term, I have S times a function of s. So I'm going to need to use the product rule. So that's just going to tell me that the derivative of this function here is going to be the derivative of s times this plus the derivative of this times s. So here I have the derivative of s is just, derivative of s is just 1. So I just have the second piece here. Then plus s times the derivative of this guy, and I'm just going to replace that by its definition. So that's the definition of capital Phi of d1 of s is the integral from minus infinity up to d1 of s of little phi of x. And so we have a formula now for evaluating this derivative. So if I'm taking the derivative of an indefinite integral, I know that it's just going to be the integrand evaluated at the upper limit times the derivative of the upper limit with respect to the variable that I'm computing. So I need to use the chain rule here. And so I'm going to end up with s, that's this s here, times lowercase phi of d1 of s. So that's this phi evaluated at the upper end point of the integral. And then by the chain rule, this is phi of d of s. So I need to also multiply that by the derivative of d1 of s. So now remember that d1 of s is equal to 10 times the log of s plus 0.015. So the derivative with respect to s of d1 of s is just going to be 10 divided by s. So 10 times this here, that's just a constant, so the derivative of a constant is 0. The derivative of the log of s with respect to s is just 1 over s, so I end up with 10 divided by s. So that tells me that the derivative of the first term now is this capital Phi of d1 of s plus s times lowercase phi of d1 of s times 10 over s. And luckily, one of the nice things about Black-Scholes is usually when you're doing it right, stuff kind of beneficially cancels out for you. So here the s and 1 over s are going to cancel each other out. So for the first term, the derivative is capital Phi of d1 of s plus 10 times little phi of d1 of s. Okay, so now let's look at the derivative of the second term. So here it's a little bit easier. So e to the minus 0.01 looks complicated, but that's just a constant. So I'm going to take that outside of my derivative. So the derivative was linear, remember. And I'm left with the derivative of capital Phi of d2 of s. And I'm just going to, so in the square brackets is just the definition of that. So that's the integral from minus infinity to d2 of s of little phi of x dx. And so I'm going to use my pricing rule, or sorry, my improper integral rule again. So that's just going to be phi evaluated at the upper endpoint. And then by the chain rule, I need to divide that, I need to multiply that by the derivative of d2 of s. And so remember, d2 of s was just equal to d1 of s minus 0.1. So this is just a constant. So the derivative of d2 with respect to s has to be equal to the derivative of d1 with respect to s. And we already computed that, and that was 10 over s. So we can recycle that result a little bit. So that's this part over here I can replace with 10 over s. And that gives me e to the minus 0.01 times phi of d2 of s times 10 over s. And so if I put all of that together, the derivative of the first term was capital Phi of d1 plus 10 times lowercase phi of d1 of s. And the derivative of the second term, so I was subtracting the second term, so it's going to be subtracted here. I have 10 over s e to the minus 0.01 times phi of d2 of s. So sorry, this d1 is a function of s, so it should have an s in the parentheses as well. I forgot to put that there. But unfortunately, we're not finished yet. So remember that little phi of x is equal to 1 over the square root of 2 pi times e to the minus x squared over 2. So what I would like to do to simplify this, instead of having a d1 and a d2 in here, I want to see if I can rewrite, because remember d1 and d2 weren't that different. d2 was just d1 minus 0.1. So maybe I can make this simpler by writing this term in terms of d1 of s rather than d2 of s. So I'm just going to start plugging things into this definition of lowercase phi. And so first of all, I'm just going to evaluate phi at d2. So I have d2 of s squared, where there used to just be the argument here. But I want to have a d1 there instead. So I'm going to replace my d2 with d1 of s minus 0.1. So I have e to the minus d1 of s minus 0.1, that quantity squared. And now I'm going to try and to make a little bit of sense of this. It would be nice if I had this just in terms of e to the d1 of s squared, because that would allow me to write it in terms of phi of d1 of s, which would make it match what's in this second term here. And so now what I want to do is sort of my completing the squares trick backwards. So let's just start by doing the math. So the first thing I'm going to do is expand the squared term here. So I had d1 of s minus 0.1 squared. So that ends up being d1 squared of s minus 2 times 0.1 times d1 of s. So I have 0.2 d1 of s. And then plus negative 0.1 squared, so that becomes positive 0.01. Let's see. Did anything change? No, I think I made a cutting and pasting error in this one, so let's hopefully that doesn't last too long. Okay, yeah, so essentially what was supposed to happen in this line, and I guess I somehow missed it, here I have 0.01 divided by 2. So that's going to be 0.005. And remember, when I'm adding things together in an exponent, I can also think of that as a product of e to each one of those terms. So what I had meant to do in this line here, I wanted to have e to the minus d1 squared over 2. That's what's going to end up here. I'm going to have minus times minus, so e to the minus, or e to the positive 0.2 d1, but I'm dividing that by 2, so I get e to the 0.1 d1. And then 0.01 divided by 2 was 0.05, and that was just going to end up also over here. And remember, there's the minus sign multiplying it here, so I have minus 0.01 minus 0.005, and that's what gives me this term here. So hopefully that would have been a little bit more clear if I had not messed up this line. But okay, and now I've written this bit, the 1 over 2 pi here, e to the minus d1 of s squared over 2. Well, that's exactly what phi of d1 of s would be. So hopefully that's starting to look a little bit simpler now. And now, remember, I had d1 was just 10 times the log of 10 times the log of s. Well, hopefully it'll show up here. 10 times the log of s plus 0.15. And so here I have e to the log of s, that's just going to be s. Because this is a sum, I could also think of this as e to the positive 0.015. So that's going to cancel out my e to the negative 0.015. Or you could also think of it as just I'm adding those two numbers together, getting e to the 0, and that's 1. So this bit here is going to cancel out this bit here. This e to the log of s, that's going to be just s. So that's going to cancel out my s down here. So what I'm left with is this second term, the magnitude of it being equal to 10 times phi of d1 of s. So now let's go back and look at my formula for the delta of c. And so the delta of c was originally phi of d1 plus 10 times lowercase phi of d1, and then minus, and we've just showed that this thing, 10 over s times e to the minus 0.01 times phi of d2 of s, that was the same thing as 10 times phi of d1 of s. So what I end up with is capital phi of d1 plus 10 lowercase phi minus 10 lowercase phi. And in the end, we find that the delta for this call option is actually just capital phi of d1.